Okay, let's get started. Any questions about assignment 6 or thoughts about the final project for the grad students? All good? Okay, so straight into lecture. While we're talking about that, remember this is a device-free zone this morning. We are working our way through our two-part lecture series on legged locomotion. So one of the things that distinguishes robots from all other technologies so far is self-motion, getting from point A to point B. And as we learn from animals and plants, there is some fundamental relationship between self-movement and intelligence. So for a lot of roboticists, the way to eventually achieve intelligent machines is going to be to start by creating mobile machines and then gradually layer intelligence on top. So we started last time by looking at legged locomotion and all the different ways that Mother Nature has come up with to get animals from point A to point B. I'll pass around Alexander's book, Principles of Animal Locomotion. You can have a look. Again, for those aspiring roboticists among you, a great book to have on your bookshelf. Okay, we'll finish up lecture 11 today and probably make our way through lecture 12, which is the mode of locomotion that we're all most familiar with, how to get around from point A to point B on just two legs. Okay. So, legged locomotion. As we started last time, whenever we're thinking about locomotion or self-motion in general, an animal or a machine is trying to strike some balance between at least these four competing aspects of behavior: displacement, robustness, how many different environments can I move across or within, how much energy does it take me to move from point A to point B, and stability if we're talking about legged locomotion. Can I do it without falling down? Okay. We started last time by actually looking at a few figures that are from Alexander's books that show very clearly that there is this interesting relationship between energy and displacement. And for whatever reason, when we start to explore this in animals or machines, the magic of embodied cognition starts to arise, which is when an animal or machine starts to interact with its environment. And in this case, interaction is not manipulating an object, but moving oneself through the environment. We're moving through a world which is really a continuum of things, but we see that these distinct categories start to arise. And in this case, the categories are gaits, particular ways of moving that feel comfortable at certain speeds, because those specific gaits have energy minima. There are certain speeds at which it is most efficient to move at that gait. We looked at humans last time, and we saw that for most humans at 2 meters per second, walking feels more comfortable than running because it requires less energy for the same amount of distance. But at higher speeds, walking becomes increasingly uncomfortable because it requires exponentially more energy compared to running. Okay. We ended last time by introducing a little bit of terminology. We have different gaits, and depending on the legged animal or legged machine we're talking about, there are more or less gaits. A gait is made up of a gait cycle, which is the orchestration of the legs that take the animal or machine back to the starting condition. So that's one gait cycle for bipedal locomotion. And during one gait cycle, we can ask what fraction of that gait cycle is a stance phase, in which there's at least 1 foot on the ground. For some gaits, during that gait cycle, there's also a flight phase in which all the feet are off the ground. Similarly, as an animal or a machine is walking or trotting or what have you, we can talk about stance foot or flight foot. Is a foot on the ground? Is it off the ground? Okay. We can also talk about stability. So some gaits are statically stable and some are dynamically stable. Well, what do we mean by that? We're not just talking about whether the animal is going to fall down, but what are the conditions under which the animal may or may not fall down. Static stability is the idea that at any point in time the animal or machine could freeze its motion and stay upright. Dynamic stability is the idea that while the animal or the machine is in motion, there may be external perturbations to its gait cycle. It may be pushed from outside. It may pick something up as it's moving. There may be some perturbation. And can the animal be dynamically stable? Can it return to the regular oscillation of its gait cycle? Well, we can start to understand whether an animal or machine is statically stable or dynamically stable by looking at its points of contact and what's known as the polygon of support. So during the gait cycle of an animal or machine, we can look to see which feet are on the ground. So in this little cartoon here, we have a four-legged animal, and at this particular point in time in its gait cycle, the left front foot, left back foot, and right back foot are on the ground, which trace a polygon on the ground. If we connect the points of contact of the feet on the ground, we get a polygon. We can then look at the center of mass of the animal, and if that center of mass is hanging within the polygon of support, then the animal is statically stable. You can again try this on your own time. So as you're walking, your polygon, what is the polygon of support as you walk? What does the polygon look like? Let's just focus on walking for a moment. During your gait cycle, what is the polygon of support that you draw on the ground, metaphorically speaking?
Would it just be a line, like connecting the 2 feet, since we just have 2 feet?
It would be, in theory, a line, but really it's sort of a thick line, right? The thing that contains both of your feet and that line during that point in your gait in which both feet are on the ground. In the case when both feet are stance feet. But of course, there are fractions of the gait cycle in which you're only on one foot. And what happens during that period? What's the polygon of support there? Just the footprint, right? So during the gait cycle, your polygon of support is a thick line defined with its endpoints as your 2 feet and a footprint, right? You're going back and forth between these. Sometimes, if you can sort of feel this if you pay attention, your center of mass is staying within that polygon of support, which means at any point in time you're statically stable, that if you stop moving, you fail to fall down. Sometimes if you're walking a little bit quickly, your center of mass will be defining the sinusoidal pattern on the ground underneath you, and it may not be perfectly within this line or completely over your foot. So if you're walking quickly and stop, you may start to fall to the side. So static stability is not really an either or thing. There's shades of gray there. But generally speaking, walking is statically stable, which is a good thing because when you're walking over ice and you start to feel your foot slip, you might stop moving, regain your balance, which literally means getting your center of mass back over your polygon of support and then continue moving, right? Bipedal walking is striking a particular balance between speed and stability. Walking is relatively slow, but it's pretty stable and it's good for moving over rough terrain and ice and other uneven environments. What does your polygon of support look like when you're running? So at one point of the gait cycle of running, you have 1 foot on the ground, so we have a polygon of support that's in the shape of a footprint. When you're in your flight phase, when both feet are off the ground, there is no polygon of support at all. So by definition, bipedal running cannot be statically stable. When you're in the air, and if you freeze all your muscles, you're probably not going to land well, right? Okay, so just 2 examples of 2 gaits, one which is statically stable, one which is not. Is walking and running dynamically stable? More or less, right? Okay, so we're talking about animals and humans. Let's see some more of the famous machines that achieve dynamic stability. This is becoming a little bit of an old-fashioned video by now, but it wasn't that long ago that Big Dog caused a big sensation in robotics and the internet in general. Here you can see Big Dog exhibiting dynamic stability. So it's exhibiting a regular gait, but you'll notice from time to time its foot slips or it steps in a little indentation in the ground and tends to recover its gait. So in essence, the world is pushing Big Dog outside of its comfort zone from time to time, and it's recovering its balance. In this video, Big Dog is carrying 325 pounds on its back. There's a good example of dynamic stability. And robot abuse, the beginning of the robot abuse video series, that's for sure. The big innovation in Big Dog was the algorithm that went into enabling Big Dog to have dynamic stability. So once a machine is pushed outside, or an animal is pushed outside of its comfort zone, what does it need to do in order to recover its balance? Maybe in the interest of time, we won't watch this whole video, but if you go back and watch it in its entirety, there's a point where Big Dog is on the ice and its feet actually slip out from under it. It scrambles and regains its balance. This is not something you want to try with 325 pounds on your back. Okay. Oh, there we go. Not bad, huh? Not bad. Okay. Very exciting and very scary at the same time for most people. Definitely not statically stable. You can probably guess that the center of mass is outside the polygon of support from time to time, and then recovers its balance. Okay, that was Big Dog 1.0. This was a video that followed shortly after, which is Big Dog 2.0, or Big Dog Beta. Not too bad, right?
In the graininess, it kind of looks like two people.
In its graininess, it kind of looks like two people, right? It is two people. So not a quadruped, but two bipeds that didn't quite do as good a job as Big Dog Alpha, but not bad. Okay. You know you've really made it as a roboticist when somebody spoofs one of your YouTube videos. So well done, Boston Dynamics. Okay. Okay, you can go watch the rest of Big Dog Beta at your leisure. Okay, that's humans, machines, back to animals for a moment. This is another figure from Alexander's book, which I think really drives home this issue about this very narrow, this antagonism between energy and speed. The faster you want to go, the bigger energy cost you're going to incur, and that antagonism, it depends on your morphology. So in this case, we're actually looking at ponies that are moving around inside their paddock. They're just doing their thing, and from time to time over the course of the day, sometimes they're walking, sometimes they're trotting, and sometimes they're galloping. The investigators recorded the natural speeds that the ponies exhibited when they were moving at those 3 different gaits. They then took the ponies and put them on very large treadmills, trained them to be comfortable on the treadmill, and would speed up and slow down the treadmill. And although as the treadmill started to go faster, the ponies would naturally want to switch to a different gait, as would you. They were trained with very tasty hay and carrots to continue exhibiting the slower gait as the treadmill got faster. So there was some training involved with the ponies to produce the 3 curves that you see in the top. And by doing that, you can see that the ponies, at least for walking and trotting, had to work pretty hard for their reward, right? They started to burn a lot more energy when they were walking at a faster speed than they normally did in the paddock, and not surprisingly, left to their own devices, they don't move at continuous speeds. They move at 3 distinct speeds, and those 3 distinct speeds more or less correspond to the energy minima of those 3 gaits, right? You can walk slightly faster and slightly slower, depending on whether you're late for class or not, but left to your own devices, you will work at a certain speed when you're walking, which happens to be the most efficient way to move in that speed range. Right? Not surprising. Okay. Okay, so let's switch now, again, back to robotics. The reading for today is actually one of my old research papers. And I wanted to explore this issue about, can we actually investigate this antagonism between these different competing aspects of locomotion? and how they change when we change the morphology. So four-legged ponies have certain gaits that they are comfortable at certain speeds, and humans have different gaits, different numbers of gaits that they're comfortable at different speeds. So the actual number of gaits and these energy to displacement curves are changed by your actual anatomy, right? The way in which you're put together influences how you interact with the world and how much energy you burn at different speeds. Okay, so what I did was to create these 10 different morphologies. You can see them all here. And I tried to keep all other aspects of the experiment the same. So remembering all the basic building blocks of an evolutionary robotics experiment, our robots have sensors and motors. So despite the fact that these 10 robots had 10 different bodies, I wanted to make sure that they had exactly the same number of sensors. If you look carefully in this picture, you'll see that each of the 4 robots has 4 A's and 4 T's, which represent the sensors. What do you think the A's and the T's represent? Angle, right? So angle sensors are proprioceptive, right? What is the angle of the joint? And 4 touch sensors. They're distributed different places in the different robots because they have different bodies. They all have exactly the same sensors. They also, each one has exactly 8 motors. You'll see 8 M's that are in there. Some of the robots have additional joints, and those joints are just frozen. They're welded together, so it's not actually a joint. It's just connecting 2 objects together. So each of the 10 robots has exactly 8 rotational joints. Each one of these robots has exactly the same neural network, which you can see here. So we have our 4 touch sensors, our 4 angle sensors, 3 hidden neurons, and 8 motor neurons. And you'll see 2 new neurons that we haven't seen before. These are bias neurons. We see 1 bias neuron that innervates or sends synapses to the hidden layer, and a 2nd bias neuron that sends synapses to the 8 motors. A bias neuron, as the name implies, introduces a bias. It just outputs a constant positive value, 1.0, all the time, regardless of what the sensors are doing. But the synaptic weights can be set by evolution. Why include a bias sensor? Why have an additional, let's just look at the top layer here. Why have a bias neuron that is also innervating the hidden neurons? What might be the use of this for robots?
Trying to combat pervasive instantiation.
Possibly. Combat. How would it combat perverse instantiation?
Try to push it towards how you actually want it to move.
Possibly. Possibly. Other ideas? So remember that these robots are going to try and use their angle information, their proprioceptive information, and their touch information. And that's going to inform the values that arrive at the motor neurons, which are going to influence the way that the robot moves, which is going to change the sensor values, which is going to change the motor values, which is going to change sensors, motors, sensors, motors. Why include a bias neuron? How might that help evolution produce gaits for these robots?
Seems like a combination of the bias and bias weights and the weights for each of the sensors could be used to weight, touch, and angle differently.
Possibly could be used to weight, touch, and angle differently. Evolution can still do that by tuning up the weights coming out of the angle neurons or angle sensors or the touch sensors. Other ideas?
Like if you look at B2, it goes to all the motor
Neurons. Yep.
So if you said, well, this leg isn't helping me, I'll turn this leg off. But these 4 legs are really helping me, so I can like amplify what's working and not.
Possibly. So the bias neuron that's innervating the motor neurons might be a way for evolution to sort of turn off some of the motors or tune up the gain of some of the motors. That could help. Other ideas? Getting closer. Yep.
Indicate the gate that you want to keep running at, just like amp everything up and make all the motions.
Okay, so we're getting close, right? You could sort of dictate the kind of gait you want, or you could sort of influence, stay away from perverse instantiation. Evolution can kind of say, I want this kind of thing. So let's try and be concrete here. Imagine that the robot, as it's moving, comes off the ground, which means all of the touch sensors go to 0, right? They're not firing. And maybe the angles of the joints happen to be close to their defaults. Remember, when you create a joint, that's 0, and any movement away or within that angle is plus or minus something, right? Imagine that they're all close to 0, all 8 sensors. What values are going to arrive at the motor layer, regardless of what the sensor neurons say, or regardless of what the synaptic weights are?
0.
0 times anything else is going to give you 0 here, and 0 times anything here is going to give you 0 in the absence of the bias neurons. Imagine that you're running and you come off the ground, so your 2 touch sensors in the soles of your feet are 0, and you suddenly freeze in the air. You cannot move until you touch down again. Again, things are probably not going to go well once you come back in contact with the ground unless you can recover very quickly. So the bias neuron at the input layer here is allowing evolution to send values to the hidden neurons even if the sensor values are 0 or near 0. It can set the pose of the robot and prepare for whatever's about to happen. Right? So bias neurons basically allow evolution, even aside from locomotion, they allow evolution to send commands to the motors even if the sensor layer is silent, near 0. Okay, that's bias neurons. Okay, so we're trying to keep everything the same. We have 10 robots with different bodies, but the same number of sensors, same number of motors. They all have exactly the same neural network. They all have these 3 hidden neurons, 2 bias neurons, 8 sensors, 8 motors. We're going to use exactly the same fitness function, which is we're just going to select for the robots to move away from the origin as quickly as possible. Question? Oh, okay. They all have exactly the same fitness function, so we're all going to evolve the robots to do exactly the same thing, move as quickly as possible. And we're going to use exactly the same optimizer, which is more or less like the genetic algorithm. We're going to create a population of neural networks, try each one out on the robot, delete the ones that get low fitness or low speed, make randomly modified copies of the ones that travel a little bit more quickly, rinse and repeat. Okay, we have 10 robots, so we're going to run the genetic algorithm 10 times, once for each robot. Then we're going to go back, reset the genetic algorithm to a new set of random neural networks, run the genetic algorithm a second time for robot number 1, again for 2, 3, 4, 5, and 6. We're going to run the genetic algorithm a total of 300 times, 30 times 10 times. We're going to do 30 independent evolutionary trials for each of the 10 robots. And we're going to see among that set of 30 genetic algorithms, what was the best speed produced by each of those 30 genetic algorithms. Okay, so betting is illegal in this classroom, but we're going to do a little informal wager. Which one is going to win? One last thing I forgot to mention. We're going to use the same optimizer and the same amount of computational effort. We're going to use a population size of, well, it's been so long I've forgotten now, population size of about 100 and run it for a couple hundred generations. So every single genetic algorithm is going to be able to try out the same number of neural networks on these 10 robots. We're throwing the same amount of computational effort at these 10 robots. Which one do you think evolution was able to evolve the furthest? And why?
I don't know. I would guess the 4-legged one in the middle top. Just because
Robot number 3?
it's got a regular shape that,
Okay.
and it doesn't have a whole lot of extra material to carry around with it.
Possibly. Okay. So 4 legs is pretty good. That's pretty ubiquitous in nature.
The second from the bottom right.
Second from the bottom right, robot number 9, the crawler. Why the crawler?
It's like naturally stable and it has the least moving parts in order to actually move.
There we go, right? Remember, stability is going to be important, and it's particularly important when we're evolving gaits for robots. Remember our discussion when we talked about evolutionary algorithms, and we introduced this idea of the fitness landscape, where we have a whole bunch of horizontal dimensions. Let's have just one for now, because I can only draw in 2D. We have one horizontal dimension, which is the genotype, the values of the synaptic weights, and the height is fitness. Right? For something like robot number 9, or something that's very stable, the fitness landscape tends to look relatively smooth. Why is a fitness landscape smooth when we're evolving gaits for stable robots?
You can't accidentally tweak a couple things and have the whole thing fall over all the time.
Exactly, right? So let's say we start here. We start with some random neural network for robot number 9, and it crawls a little bit and then comes to a stop. So not great, but not bad, right? Then evolution tweaks the neural network or performs some mutation, and the machine crawls a little bit faster, or it crawls a little bit slower, right? We have a smooth fitness landscape. What do you think the fitness landscape looks like for robot number 10?
Really sharp peak.
Right? So the vast majority of neural networks that you could place inside of that tripedal robot, or I didn't even bother including a bipedal robot because that's really difficult. We'll come to that in the next lecture. Most of them are going to cause this statically unstable machine to fall over, right? Think about the polygon of support for robot number 10. In this picture, the polygon of support is a very narrow triangle. The minute it lifts one of its 3 legs, that polygon is going to become very, very small. It's going to be very unlikely that its center of mass is inside that polygon of support, and over it goes, right? It falls. There are many, many neural networks out there that will produce a fast, efficient, robust gait for the triped, not unlike something you saw for Big Dog, but they're hard to find, right? This is known as the needle in the haystack problem, right? Those neural networks are out there. We're proof that they exist. They're just hard for evolution to find.
Just a question.
Sure.
So does 5 kind of move like a caterpillar?
I will show you videos of these in a moment, but yes, it moves like a caterpillar. So all of the 8 motors in the snake robots, 5 and 7, have joint normals that are pointing out of the side of its long axis. So they're all rotating. It's moving in and out of the plane defined by its body.
Did they ever like try to move what like more like a snake as opposed to a caterpillar? You know what I'm saying?
They cannot, because I'm fixing the joint normals to be to the side. All they can do is move within the plane, right? So nothing like the fancy snake locomotion gaits we saw last time. Any more bets?
Or just a question.
Sure.
But it's for the needle and haystack problem.
Okay.
Just in general, like, so if we're just looking for a robot that can eventually have a neural network that can let it do its task that we
Yes.
want to do, then like, isn't it not really a big deal if we have to run it even like 100,000 times, as long as we can find that neural network eventually, you know?
Yeah, sure. Okay, so even if it's a needle in the haystack problem, why don't we just run it for longer in order to find it, right? The problem is I'm drawing in 2 dimensions, right? So this is a little bit misleading. You have to think in terms of 200 dimensions. If we have, well, let's see, how many dimensions do we have here? However many arrows there are in this picture, each one of those arrows has a synaptic weight associated with it. That's how many dimensions there are in the fitness landscape. Imagine a peak sitting in a very high dimensional space. The fraction of poor solutions to good solutions that goes up very fast as you go up into high dimensions. So in this picture, yeah, of course, 100,000 would be enough to find it. In 2 dimensions, maybe 10 million solutions would be enough to find it. In 3 dimensions, it gets hard really fast. And this is something that crops up from time to time in math in general, but AI in particular, which is the curse of dimensionality. We often build up our intuition by looking at things in 2D and 3D, because that's pretty much all we can wrap our minds around intuitively without the support of math. And we then extrapolate to higher dimensions, and things usually don't extrapolate well to higher dimensions. So yes, in theory, we could throw enough computation at something to find the needle in the haystack, but in practice, very, very difficult to do. Question?
Question about robot 2. So that's pretty close to like a lot of four-legged animals.
Yes.
How much, like, have you made one where like that, it has like an elbow there as opposed to like that being a foot and then it has another, part down and touches it? Does that increase it? Would that increase the speed that it runs a lot faster?
Maybe that's exactly what we're trying to do in this study, right? What if we make changes to the morphology? What impact does that have on evolution's ability to find good gates for it? So when we create a given morphology, unbeknownst to us, we are setting the ruggedness of the search space that evolution is going to have to traverse. And this is one of the big challenges in evolutionary robotics in general. Once you build a machine and you try and optimize a controller for it, how easy or hard is it going to be to do that? We don't know. We don't have a good understanding of the relationship between anatomy, neural control, and these 4 aspects of legged locomotion. Still kind of an open problem. Anyone else want to lay any other bets before we move on? We have one for number 9, number 3. Someone else?
I feel like number 10 could get the, I'm forgetting what it's called.
The needle in the haystack? Oh,
Well,
no?
yeah, it's the kind of needle.
Okay.
It's not like swinging your leg when you walk. If
Maybe.
you can do that with its middle leg, it can go really quick.
Maybe.
Go 4.
Why 4? Just because?
Just want to take a bet.
Okay, fair enough.
I'm thinking number 8 because it might be able to use that long snake-like the trail that it has behind it to abuse its momentum to sort of swing itself forward.
Possibly, right? We already saw the brachiating robot that was able to use its battery pack for momentum. Maybe that's possible on land. Yeah. Number 2. Okay, do we have a bet for everything yet? Not quite. All right, remember your bets. Okay. Here's a little bit of a hint. Okay. What you're looking at in each of these pictures, these are 10 footprint graphs. Part of the reason why I wanted to show this to you is this is a nice visualization tool for you to use in your final project. It's a nice way of showing in a static picture something that's often shown in a movie, which is the way in which the robot moves. So before you get to making movies of some of the robots you evolve, you can make footprint graphs which show pretty well or how poorly the robot is moving. Okay, so 10 footprint graphs. Each one shows the actual movement of the best neural network found for that robot, right? Robots 1 through 10. So we did 30 evolutionary trials for each robot, and among those 30, we took the 30 champions, the ones that had highest fitness, and among those 30 champions, we then took the grand finalist, which was the neural network that produced the fastest gait.
So presumably you put a touch sensor in each of the feet and you've only connected up 4 of them to the neural network because you've got more data than touch sensors, right?
There's the touch sensors in the feet. Are you talking about for the tripod?
Well, right, you've got 4 touch sensors, right?
Yep.
But in some of those graphs, you've got 6.
Oh yes, I'm sorry, right. So this is not reporting the touch sensor information. This is reporting just contact between any object in the robot and the ground. So you can see there's actually 4 points of contact here for the tripod, but the third point of contact very rarely touched the ground. Yep. Question?
Sorry, how do you read this?
Okay, so let's do an individual footprint graph. So this graph here is showing the best neural network for the tripedal robot. Okay, each row corresponds to one of the objects that came into contact with the ground while this particular neural network was in control of the tripod, which was probably. Let me use the mouse here, it's a little bit easier. It's probably this object, this object, this object, and this object. In this one here, how many are there? 1, 2, 3, 4, 5 objects that came into contact with the ground. That's robot number 9. And if we look at robot number 9, sure enough, there are 5 objects which are likely to come into contact with the ground. 1, 2, 3, 4, and 5. Make sense? Okay. For robots 5 and 7, the 2 snake robots, as you would expect, robot 5 and 7, there are many more rows corresponding to each of the objects along the length of those snake robots. So each row within each footprint graph corresponds to one object in the robot, and each column corresponds to one time step during the 500 time steps over which we evaluated that neural network. Question?
Well, just kind of comment.
Yep.
Trying to analyze this to see whether which one's the best. Would it be kind of the least amount of black area over the total?
Possibly.
But
Yep.
the most number of points?
Possibly. So the most number of points, but the least amount of black. So black is when that particular object came into contact with the ground at that particular point in time. Right? That's what the black and white pixels represent. So your comment is, maybe if we see a lot of white, what is it that the robot is actually doing?
It's in the air.
It's in the air, which is the what part of the gait cycle? The flight phase, right? So if we actually look, for example, at this point in time in robot number 9, during this period, the robot was in the air, right? This was the flight phase of this particular gait. I don't know what this gait is. And at other points, if we draw a vertical line and we touch the black pixels, that's the stance phase. One or more of the objects making up the robot was in contact with the ground.
But the problem with the ones with the large, like white space, like 8 and 9,
Yep.
is that it looks like they have movements where they're trying to rebalance. It's like, wouldn't you want the ones that have good repeated gaits?
Wouldn't you want ones that have good repeated gaits? So the footprint graph shows you which object was in contact with the ground at which point in time. It does not show you distance, right? So these could be robots that are simply hopping in place and getting very low fitness. We know that they're probably not, because we're drawing the footprint graphs for the champions, the ones that got the highest fitness overall, right? So this is showing you something other than how far the robot traveled, right? One of the things it's showing you is, do these gaits have a flight phase, yes or no? And the other thing you can see, and the main reason for the footprint graphs, is you can see the cleanliness of the oscillation. How clean is the gait, right? Some of these are oscillating more regularly than others. Which ones?
2.
Okay, 2 looks pretty clean, right? Who bet on 2? Someone bet on 2. Well done. Okay, so that's looking good. Still not sure that that's the winner, but not bad. Anybody want to revise?
Good to me.
What's that?
3 still looking pretty good to me.
3 is
For
still looking pretty
regularity.
good to you. Yeah, that's pretty clean.
6 also isn't bad.
What's that?
6 isn't bad.
6 isn't bad. Okay, 6 is the hexapedal robot, right? Okay, no one placed any bets there. How are the snake robots doing? 5 and 7. Not great, right? There's some sort of regularity there, but it's pretty dirty.
Do the robots optimize over the length of the test, or is it once it's done?
It is, that's a good question. So did we calculate fitness at the 500th time step, or did we sum up fitness over the entire lifetime? We took it at the end.
Isn't it important to know how fit it is at a given momentum level?
Possibly. In this case, we just said at the end of 500 time steps, you better be as far from the origin as possible.
I'm liking number 6.
Okay, here's some changing of bets here. One last hint. Let's have a look at a few of the gaits. These are again the best from 4 of the 10 robots. Again, I apologize for the quality of these videos. They're a little old by now. Here's the hexapod. Not bad. Robot 2. It's a quadrupedal gait you don't see too often in quadrupeds, but it is possible. Not bad. Here's the triped. You'll notice it's actually found a pretty stable gait, right? It's making a larger polygon of support by keeping its two outer legs behind it up to a point. Recovered there a little bit. It's dragging, yes. And loses the plot right at the end there. Cut! Okay. One of the snake robots. Again, remember, these didn't have very clean oscillations. You can see some sort of oscillation. If you look carefully, you'll also kind of see these traveling waves moving back and forth along the length of the body. What mode of locomotion is this? Peristalsis, right? So if you look in the lower animals, the first animals to move in soil or to move on land, most of them exhibit peristalsis. Most of the time, if you create a robot that has enough parts, I guarantee you will see artificial evolution rediscovering what Mother Nature discovered billions of years ago, which is peristalsis. Get everything to move one after the other in a traveling wave, and that will usually produce momentum in the opposite direction. It's not perfect, but there you go. Okay.
So is the caterpillar robot keeping its balance, or is it just because it's in that perfect simulator that it's not falling?
I cheated a little bit. If you look at the feet, they're very small cylinders on their side, so they're not spheres. Can't fall over. Obviously, the triped can. Okay. Any last revisions of bets before we move on? Everyone comfortable? Okay.
There's not a whole lot riding on it, so.
Not a whole lot riding on it. Okay, here you go. So, 10 fitness curves. I was using a machine back in 2002. This was a lot of computational effort, so I didn't finish all 30 runs for robot number 6. That's why that particular curve looks a little bit more ragged than the others. So each of these 10 curves, each one of these 10 curves is an average over 30 other curves, which were the 30 curves produced by the 30 genetic algorithms for robot 7. So these fitness curves look very smooth because they're averaging across 30 other fitness curves. So robot number 6, I didn't get all 30, so it's a little bit messier. Okay, some of you got rich, some of you didn't. Okay, so robot 6 and robot 2 and robot 3 more or less seem to end up in more or less the same place. They were clearly tied for gold, and then there was a second group there, and then our poor snake robots here did very poorly indeed. Questions?
Interesting, we don't really have any hexapedal animals that are really fast.
We have lots of hexapedal animals that are really fast.
We have insects, but no, like cheetahs.
True, right? This is an interesting question that's known as the emptiness of morphospace. This is something studied by biologists, or it's a big mystery in biology. Morphospace is not a fitness landscape or a fitness space. It is a high-dimensional space that contains all possible biological body plans. So it's basically an infinite space, right? Humans occupy some small point in morphospace, horses somewhere else, beetles somewhere else, protozoa somewhere else. And most of the space, at least here on Earth, is empty, right? Why are there no large hexapedal animals? There are small hexapedal animals and large quadrupedal animals, but nothing sort of in between. Now, is that just because Mother Nature hasn't got around to it, or there's something fundamentally inefficient about large hexapedal locomotion? Who knows?
Don't hexapedal, like having more appendages requires more energy to constantly manipulate, and
Maybe.
a lot more brain power, meaning more energy to power brain to power.
That's one hypothesis, right? So 4 legs more or less is enough to maintain enough stability. Actually, 3 legs is enough, right? You can sit on a 3-legged stool. So do you need extra legs, right? It's certainly extra mass, and that's probably going to require more energy. However, remember that as long as our bodies are up in the air, we can swing vertically, so maybe these legs can act as pendula. The answer is it's not so obvious, right? There are these very complex interactions between total mass, exploitation of momentum, how fast you need to move, different kinds of gaits.
Just to kind of talk against that point, it's just like, well, what if we had cheetahs who also had arms that could grab and tap, like while they were running on 4 legs?
Maybe.
That would be scary.
Okay.
Like for
There are a lot of,
survival.
yeah,
Maybe
there are lots of,
all that.
there are lots of cool body plans that might exist in parts of the morpho space that aren't here. And again, we could spend the rest of the semester digging into that question. So one more point about that.
Well, no, I was just
Okay.
curious about these robots. Did you calculate energy expended?
Okay, so now to end this lecture, we're going to end by trying to answer this question. What is it about the morphologies of robots 6, 2, and 3 that allowed them to win and the others to do so much more poorly? So now we've answered the first question, which is clearly there is an impact of morphology on the ability of evolution to produce fast locomotion. Our fitness function was just displacement. We didn't select for energy efficiency, so that doesn't really matter for these robots. Some of you have started to build up a bit of an appreciation for these physics engines and how things work. What sorts of aspects of the morphologies of 6, 2, and 3 might have tipped the balance in their favor?
Less friction because there are just points on the ground at any given time as opposed to dragging tails or something.
Possibly, right? So the ones that were on the ground are more stable. They're down low, but like the snakes and lizards we talked about last time, they're often dragging. And although there is no penalty here for energy efficiency, the moment you're dragging, you're also being slowed down. So pyrosim simulates friction. That's going to slow you down. Other ideas?
I feel like those 3 have the best center of mass, like compared to the legs and how much motion the legs can.
Okay, so maybe it's about the ability to maintain the center of mass over a polygon of support as a function of number of legs.
I think it's really interesting that 4 did so poorly.
That 4 did so poorly.
Because it seems like that would, at least be in the upper echelon of, compared to 2, 3, and 6.
Possibly.
Oh, I mean, yeah, sorry, 3. Sorry.
6, 2, and 3. 6, 2, and 3. Right. Okay. So 3 is one of the winners, and for those of you that have moved on to assignments 8, 9, and 10, that's what you're building, and that's the reason why. That one tends to be a pretty good solution. Easier to build robot number 3 than it is to build robot number 6. Okay. So I asked those same kind of questions in this paper. What is it about the aspects of the robots that allowed some to do better than others? And I tried to answer this question by taking different features, like the total mass of the robot, or the total number of points of contact that could come into contact with the ground, and plotted those features from low to high. So I reordered the 10 robots, and the vertical height of each of these boxes is the average fitness of the 30 champions from the 30 genetic algorithms run against robot number 1, robot number 4, robot number 8, and so on. Does total mass matter? Not really. There is seemingly this sort of decreasing trend. The heavier you are, the worse you do. But there are 2 notable exceptions. 2 and 6 are pretty heavy robots, but did very, very well. So mass, just the total mass is not enough to dictate that. So having 6 legs, having more mass, that doesn't necessarily count against you in every case. Like in your assignments, every object is 1 kilogram, so you can figure out the mass of these robots just by counting up the total number of objects. Okay. What about points of contact? Does that matter? So it seems that there's kind of a sweet spot, right? So too many points of contact, like 5 and 7 over there, and it's probably overkill. You don't need all those points of contact. And the triped, which is over here to the left, robot number 10, has 3 points of contact. It's too little, right? You end up with the needle in the haystack problem. So there's sort of some sweet spot in between, which is interesting because one of the most successful species on this planet has 2 points of contact, but locomotion is not the only thing we do. So whatever the answer is, again, it's not simple. It is a combination of mass, points of contact, issues to do with friction, how easy it is for evolution to exploit momentum. It's a lot of things, whatever the real answer is. Okay, last thing I wanted to look at is relationships, again, between body and brain. So I took the 10 robots again and arranged them again from 1 through 10. The light gray bars show you the data that I just showed you, which is how well evolution can get these things to move, their average performance or their average fitness, with the neural network that has 3 hidden nodes or 3 hidden neurons. I then did an additional 300 runs where now everyone had 5 hidden neurons. When we talked about neural networks, one of the things we talked about is it's hard to know how many hidden neurons you need for a given problem. How many hidden neurons these robots need, I don't know. But clearly going from 3 to 5 hidden neurons helped. Right? In general, the robots traveled faster for the same amount of computational effort. Most of the error bars overlap, which means maybe there was a little bit of an increase. Maybe it wasn't that significant. There was some. There's one robot in which there's no overlap. Which robot was that? Which is the...
That's one of the snakes also.
It's one of the snake robots. You can tell because 5 and 7 have low bars, right? So for some reason, adding hidden nodes helped the snake robots more than it helped the other 8 robots. So yes, the dark gray bars are higher than the light gray bars. It helps in general, but it was definitely more useful for some morphologies than others. As always in science, answering one question raises 10 more. So why did the snake robots benefit more from more neural real estate? Hard to say. One thing which is maybe not so interesting is because they're already doing pretty poorly, so any help is much appreciated, right? The very fact that they're doing poorly probably meant that it was more helpful to get some more neural real estate.
Also, why can real worms move around with very little brains?
They move around with very little brain, right? So the worm in quotation marks. These are not like real worms. Okay. Hard to say, but the worms in this one definitely need to produce this peristaltic motion, and it's probably the case that this kind of neural network, it's hard to produce peristalsis in something like this. Maybe if you increase the hidden layer, it gets easier for evolution to produce peristalsis for the worms.
So by adding more thin layers, is that, I guess for the worms at least, increasing their memory capacity so they can try to, did they have better standing waves and stuff when they're...
They did have better standing waves, so there was cleaner peristalsis when they had 5 hidden neurons. Now was that because, like what you just said, we added 2 more hidden neurons, which means there's many more recurrent connections, which means there's more memory, and that may be useful, because if I'm one segment of the worm robot, there's timing issues, right? The segment behind me has to flex, and then I have to flex not at the same time, but slightly before or slightly after, right? This is like doing the wave in the stadium. You have to time things to make sure that the whole pattern flows. So recurrent connections, which give you memory, probably helps evolution with timing different motions within the same body, and that's probably why it helps. Okay. Yes?
For something like the hexapedal robot, so we put evolution on it, we let it do its thing, and I guess maybe let's say it finds an algorithm that's walking, running, and whatnot. It has the legs alternating pretty close to like in a few different groups,
Yep.
Slightly different times. Do you ever go in, or like does the algorithm incorporate like going in afterwards and like directly syncing up the times of a few legs swinging in opposition?
We could do that. So we could go in after something has evolved and kind of clean up the gate. We could do that. one of the easiest ways to do that would be to modify the fitness function to select not just for forward locomotion, but for things like you mentioned, right? That certain subsets of legs should move together and others should move out of phase with one another. When we used to have a midterm and a final exam in this class, that always showed up on the exam, which is write down a fitness function that selects for galloping or trotting or a peristalsis. Assuming that in your fitness function you had access to the values of the sensors at every time step. So something, imagine your fitness function could see something like this data. What would be a fitness function that would give a high number when, for example, the triped is moving its outer legs in sync and the two outer legs are moving in antiphase with the middle leg? And then it should also give a value near 0 when it's doing anything else, right? So if you're interested in this, it might be worthwhile just with pen and paper sitting down and trying to write a fitness function that selects for a given gait. It's a good question. Okay. So again, just to conclude this lecture, unfortunately there are no easy answers here, right? In order to get from point A to point B, any animal or machine needs to strike a balance between these 4 competing demands and the kinds of trade-offs that any given machine can make between these 4 demands is a function of its physiology, of its body. That matters. Remember also that self-motion and intelligence seem to be fundamentally connected with one another, at least in biology. That's where intelligent animals got their start, self-motion. So the body makes it easier or harder to produce locomotion, which may then lay the groundwork for intelligence. So this again clarifies that there is this fundamental link between the body and intelligence. We feel like intelligence is something that just happens up here, body doesn't really matter, but thinking about thinking is misleading. Okay, so that's legged locomotion. Let's move on to a locomotion that's a little bit more familiar. All of you can walk and run. Why only 2 gaits? Some of you are laughing already. That's a good sign. Turns out, of course, if you're a biped, there are many more ways to move other than just walking and running. One of the greatest bipeds of all time, doing what he does best. Okay, where's this video from? Monty Python. Which particular skit is this in Monty Python? The Ministry of Silly Walks. And if you know anything about the British government, they have a ministry for absolutely everything. So clearly there must be somewhere in Whitehall in London, there must be a Ministry of Silly Walks, and here's one of the ministers on his way to work. Okay. Never gets old. You can go and watch the rest of the video. Why, aside from the ridiculousness of it, why don't we walk with a silly walk? Why walking and running?
Silly.
Because it's silly.
It's not energy efficient.
It's not energy efficient, right? You can be sure that John Cleese was sweating bullets after this skit. Not an easy thing to do. In the privacy of your own dorm room, you can go and try this for yourself. Back when humans had predators, right? Predators also love to see people walking with silly walks, or at least walking with a limp. The moment you're walking with a limp, what does that mean? From the predator's point of view? Your food, right? You're not energy efficient, you're wasting energy. So even if you can move quickly with a limp, if I'm a predator and I'm not limping, I will eventually catch up with you, right? So there are very strong selection pressures that favored energy efficient movement for bipedal locomotion. It's another open question in biology or maybe anthropology about why we ever got up on our hind legs in the first place. Quadrupedal locomotion, someone mentioned cheetahs already, is pretty fast. We're not as fast as cheetahs. Why did evolution select for bipedal locomotion?
I was just going to ask.
Yep.
There was no robot that we looked at that had like the gait of an ape.
Not yet. You will in the next slide.
It could still possibly be for energy efficiency, because humans are naturally the long distance runners.
Long distance runners and long distance walkers. So one theory in favor of bipedal locomotion is it's about endurance. There are many others, and it may be, as usual in biology, sort of all of the above.
I think it's because we can walk and we can use our hands.
Right? So the minute if you're a quadruped and you start to evolve the ability to get up on your hind legs, suddenly you have these things available for other things. That's another hypothesis. There's another reason evolution might have favored bipedalism.
Also robustness. I mean, there's a very wide variety of terrain that humans can move over that other animals can't.
Maybe bipedal locomotion increased the robustness of our species. There were more ecological niches that we could move in, on, or through.
Mammals that have larger brains tend to have a closer to 90-degree angle of insertion of the spine in the foramen magnum.
Okay.
So that also allowed us to have a bucket pelvis.
Okay, so there's also anatomical reasons, right, having to do with pelvis, brain case, spinal cord.
Has anyone mentioned energy efficiency?
We mentioned energy efficiency, endurance walking. So on half a Big Mac, you can walk, depending on your level of fitness, a long, long way.
We can dance, and that's fun.
Okay, we can dance, and that's fun. Might also be a way to attract a mate. That is also one of the hypotheses. Yeah. Missing one important one. Think about where our ancestors evolved.
So we can see farther. That might be helpful.
If you happen to be in a savanna where there's lots of tall grass, one good thing to do is to get up and be able to look over it if there's no trees around. Again, this is a question that has no answer yet. Clearly, we did pretty well as a species. There was selection pressure favoring for bipedalism. It's an interesting question. We'll leave it there for now. Okay. What part does the upper body play in locomotion? Of course, once you walk on your hind legs, you can use your hands for object manipulation and other things. Balance, right? So when you're running at your top speed, your arms have to pump in opposition to your legs. They move in antiphase. Why? They maintain balance, but specifically, how do they maintain balance? Torsional, right? Again, find somewhere where people can't watch and laugh at you, and try running at your top speed and don't pump your arms. You will twist and fall down, right? So again, lots of interesting things going on during bipedal locomotion aside from just energy efficiency. Okay, so someone said, why haven't we seen, this is not a primate robot, but a humanoid robot. This is Asimo. This is an older video at this point, but this was state-of-the-art at the time. Seems really excited, yeah, or nervous, or who knows what. Okay. Was that running? Remember our discussion about running? Is it running? It looks like running. Look carefully. It's not how you run, hopefully.
I don't know if there's actually a flight phase, though.
There's no flight phase. So if you watch carefully, the feet are always in contact with the ground. Why? Why didn't they program Asimo to have beautiful, long, and high flight phase?
That's really hard.
It's really hard and probably very expensive if something goes wrong.
There's no stabilizing muscles.
There's some stabilizers built in there to some degree.
But they don't want to fall over and break.
They don't want it to fall over and break, right? So the designers of Asimo are striking this balance between those four competing demands. So you can get high speed and maintain stability. That's Asimo is increasing stability and increasing speed. There's a tiny little bit. Yeah, it's a little bit. So they're increasing stability and increasing speed, but that means they have to pay a heavy cost in terms of the other two. What is the cost that's being paid here? Why don't you run like that? It's very stable, very fast. What's the problem with it?
Well, the first thing I noticed, like, it bent its knees and it can't take giant steps.
It's bending its knees and it could, but it's refusing to do so to increase stability. So those are all things that Asimo or the designers built into Asimo to increase stability.
Once you get above a certain speed, isn't it more efficient to run?
It's way more efficient to run.
What about obstacles?
Obstacles, all right, forget obstacles, forget all of that. Look at the backpack. This thing is wearing a backpack. What do you think is in the backpack? A battery. That's a battery. It's a 50, 100-pound battery on Asimov's back, which, again, battery technology 15, 20 years ago wasn't great, but Asimov would flat out its battery within, a few minutes. Very stable, very fast, exceedingly energy inefficient, right? That was the deal that the designers struck in making Asimov.
It does look like how you'd run on ice, though.
Yeah, that's how you might run on ice, which allows you to keep moving quickly and be stable, but you pay a cost for doing it also. Yes?
Does it have like a spine kind of thing? Like I know if you think like about us running with a backpack, we can lean forward, but if it can't, then it would have to compensate for that.
It has some ability to move its center of mass over the polygon of support. One last question about Asimov, and we'll move on.
Yeah,
Yes.
sort of off the running on ice thing, I noticed that his ankles really aren't moving much, and he's not rocking off.
Exactly. So there's also a cost being paid here in robustness. So Asimov works great on flat ground, not so much on other terrains. So I was actually in Japan when there was a public demo of Asimov, and they had a set of stairs that was made specifically for Asimov. They would wheel the stairs out, and Asimov would go up the stairs. Asimov worked for those stairs, but not these stairs. No other stairs except the ones designed for Asimov. And even still, it got halfway up and fell backwards, and the show ended immediately. So. Okay, again, very impressive for the time. The point I want to make here is, again, they struck this very extreme balance between these four objectives. Let's look at another robot now, which is at the opposite extreme. Okay, again, bipedal locomotion strikes a very different balance between these four competing demands on bipedal locomotion. How is this robot different from Asimov? The center of mass is?
A lot lower.
I think it's a lot higher, actually. Well, it depends. Asimov had the battery on the back. Not so much about that.
Using momentum.
It's using momentum.
Narrow frame and giant feet.
Narrow frame and giant feet, yes. What else? There's lots of differences.
It looks like there's nothing controlling it other than like wires and counterweights.
There doesn't seem to be anything controlling it, right? Where's the battery pack? There's no battery pack. There's no battery. There's no motors. There's no sensors. There's no neural networks. There's no electronics at all. There's a few springs in there. This is a completely mechanical device. So depending on your definition, this robot is infinitely energy efficient. How is this possible? Where's the energy to get this robot moving coming from?
I imagine it must give it a little nudge to get it going.
Not quite. They actually have to put it in a very specific configuration to get this work, but there is no energy imparted by the human handler here. So we're back to high school physics. What's going on here?
Incline or decline?
Yeah, exactly, right? It's not walking on the ground. It's walking down a very shallow decline, and by doing that, this mechanical device is translating potential energy at the top of the decline into kinetic energy, right? Back to high school physics. How much money did it make to build this robot? In terms of people power, human resources, pretty expensive. Took a lot of grad students a lot of time to make this. I don't know, maybe by today's standard, $20 worth of parts at the hardware store, right? Cheap to build, cheap in terms of energy, moves not too slowly, it's not too bad, extremely energy efficient, looks great, right? But again, there has to be a cost here somewhere, right? What is the cost? It's not robust at all, right? This robot has its own decline, which is, I can't remember what it was, 3 degrees, 2 degrees it doesn't work, 4 degrees it doesn't work, flat ground it certainly doesn't work, rugged terrain, forget about it, right?
It's kind of like Asimov's stairs, right?
It's like Asimov's stairs, right? So they're both very fragile, they both have little to no robustness, okay? But two very different approaches. They stand at two sort of opposite extremes in this trade-off. Okay, so the robot you saw in the top left, this is the passive dynamic walker. So it's completely passive. There's no actuation. There's no active pushing from motors at all, right? There are no sensors, no neural networks whatsoever, and it's walking down a declined plane, which is a nice place to start, perhaps. We might want to start with that extreme trade-off, and again, now try and work in the opposite direction. So a few years after the passive dynamic walker was demonstrated at Cornell, another group in the Netherlands demonstrated a hybrid dynamic walker. And the hybrid dynamic walker is going to use passive dynamic locomotion again. It's going to exploit the fact that vertically swinging legs can exploit momentum. But during a particular point in the gait cycle, there's going to be a little kick, a little impulse force from a motor, and then the motor is going to go silent again. This robot has an empty bucket for a head, which is meant to symbolize that there isn't a lot of electronics here, right? There's not a lot of brains in this machine. It's walking on flat ground, so we've increased the robustness of this kind of machine a little bit. If you were building this machine, when in the gait cycle, and where would you apply the impulse force? Where would you want to push the leg of this robot? At the very middle, yeah, perhaps. That's one possibility. We can do a little better than that.
The back of the steps?
The back of the step, right? Think about your own walking, and again, attend to your walking as you walk about campus today. When your foot is at the back, you can let go and it will swing forward, but you also give it a little bit of an impulse force to kick it further forward to catch yourself and keep going, right? So the passive dynamic walker is basically doing this, and if you want to keep this going, just give a little bit of a kick when you're at the back and push it forward, and it will continue on its own merry way. Okay, so that's the passive dynamic approach to bipedal locomotion. And we're running out of time, so we'll just, in the next few minutes, we'll just start in on the experiment for this lecture, which is to try and answer the question of, instead of building these machines by hand, which is extremely difficult to do, it took years of a grad student effort to do this, can we evolve a robot to exhibit passive dynamic walking? So no motors, walk down a decline. Once we evolve a passive dynamic walker to do that, can we then continue evolution and gradually widen the environmental envelope for this machine? Can we increase its robustness a little bit and translate it from a passive dynamic walker into a hybrid dynamic walker? So here's the passive dynamic walker. And here it is on flat ground. And again, unfortunately, these authors didn't get any videos of this, but you can sort of figure out how this is going to go. Okay, so let's start by introducing some aspects of this robot. At the beginning, we're going to evolve a passive dynamic walker, but everything we've seen, every experiment we've seen to date in this class, the experimenters were evolving the neural network. But there is no neural network here, so what do? Instead, we're going to evolve the morphology of the robot itself. We're going to start with this very basic bipedal frame, and evolution is going to be able to move these masses that are sort of lead weights attached to different parts of the body, which change the mass distribution of the robot, and therefore is going to change the ability of evolution to produce passive dynamic walking. Okay. So what do we have in terms of joints? So we have two legs and we have a hip where we have 2 degrees of freedom. So obviously the leg needs to be able to swing forward and back, and the leg also needs to be able to swing outward and inward towards the other leg. The knee, like our knee, has just 1 degree of freedom, a rotational joint, and 2 in the ankle, one that allows the foot to go up and down, and the other one that allows the ankle to twist left and right. We can also do this a little bit, but in this case, we're just going to focus on these 2 degrees of freedom. So in any one leg, we have 5 joints, but these joints are passive. There's no motor attached to the joints. It's just a ragdoll robot. Okay. Here's the robot itself. So there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 variables here. And these 12 variables are going to become 12 genes that evolution can play with. And they're going to dictate the position of these three masses, the mass at the waist, the two masses that are on the thighs, and the two masses that are on the shanks. They're also going to add and move around some mass in the foot. XT, YT, XS, YS. These are where the masses are actually placed on the shank and thigh respectively. Foot length, waist radius, and finally BY, which is the starting hip angle around the y-axis. So one leg is going to be rotated relative to the stance foot, which means that the robot is going to start with one stance foot and one flight foot, and we'll see what happens with this robot next Tuesday. You have a quiz due tonight. Have a good weekend.